Greetings from BMS College of Engineering, Bangalore. This is the second module on sampling theorem. So today, in this module, we shall see two concepts. One is the natural sampling, and the second is the concept of aliasing. So in the previous module, we'll have a quick recall of the sampling theorem. The sampling theorem states that given a continuous time signal x of t, that is band limited, if we have the samples of x of t, we can recover back the original message signal x of t from its samples, provided we ensure that the sampling rate is satisfied as recommended by the sampling theorem. This is a statement we saw, and we also tried to prove the theorem in the previous class. So what we had was, if I have a signal x of t, and a continuous time signal x of t, I multiply this by an impulse train, which is a set of impulses that maintains a fixed time interval, is periodic and maintains a time interval Ts. I get my sample signal x of t, and this is how my sample signal is going to be. And since we are multiplying it by t of s, by p of t, which has a sampling interval Ts, my sample signal also will be having the same sampling interval. Now this is the sample signal, and the sampling theorem states that from this x of t, we can get back the original message x of t. And this we saw by moving into the frequency domain. We realized that if I take my sample signal and if I pass it through a low pass filter, my output of the low pass filter is going to be my message back. So I am going to get this. This was the theorem, and we also saw that if my spectrum, if x of omega, if my original signal x of t has a spectrum that is band limited to say to W, then the spectrum of the sample signal, the spectrum of the sample signal xs of omega is going to be periodic with period omega s, and all this is what we have seen. So the spectrum of the sample signal xs of omega was given by 1 by Ts sigma n equal to minus infinity to infinity x of omega minus n omega s. So what we saw is, the moment we sample a signal, if I sample the signal, that is, if I make the signal in time domain discrete, if the signal becomes discrete in the time domain, in the frequency domain it becomes periodic. In the frequency domain it becomes periodic, and the period is omega s. This is what we have seen. And to get back my original signal, all that we have to do is to pass my sample signal through a low pass filter with a cutoff omega c. And we also saw the condition, the omega c has to be greater than W. Omega c, the cutoff frequency of a low pass filter, needs to be greater than W and has to be less than omega s minus W. So then we get back the signal. Now there are two requirements in this whole sampling theorem to function correctly. And one is we are multiplying it by an impulse train. And the next is we are assuming the signal is band limited. Let us see whether these two requirements create any issues in actual implementation of the sampling theorem. So we shall now take of using a pulse train instead of an impulse train. Let us say I have my signal x of t. I have my signal x of t, and then I need to multiply it usually by an impulse train and to get my sample signal xs of t. So instead of having an impulse train, I am going to use a pulse train p of t. And what is my pulse train? These are going to be pulses of fixed duration, of a finite duration, because this is feasible. To have a pulse of zero width becomes not a practical implementation, and hence we normally have a finite duration. Let us say the duration, the width of this pulse is delta t, and we still retain the sampling interval as ts. Now let us see what happens to the sample signal and how is my spectrum of the sample signal. So I have my sample signal x of t, and in this case my sample signal xs of t now results in what is known as the natural. So I am going to have it is not drawn to scale, it's not drawn, it's just a freehand drawing to help understand the concept. And each of these samples are going to be of width delta t. And we still have the sampling, the interval between two samples as t of s. This is what I get now when I use pulses of finite duration for getting the sample signal. And this output is also known as the natural sample signal or natural sampling. So now we need to compute the, as seen earlier, it is not possible to tell whether this natural sampling or the finite duration of the pulse is actually going to create any issue, or can we still recover back the message from the sample signal. To understand that, there is a need to go into the frequency domain. So now let us consider, once again we try to get the Fourier series representation of the periodic signal, and that is given by n equal to minus infinity to infinity p of n, the Fourier series coefficients, e to the power of jn omega s t, where omega s is 2 pi by ts, the period at which the period of the periodic signal. And p of n, known as the Fourier series coefficients, is given by 1 by ts integral over one interval ts p of t in one interval e to the power of minus jn omega st dt. And this makes it 1 by ts. Now say delta t by 2, since my pulse width is of my pulses are of width delta t, and I consider the interval from minus delta t by 2 to delta t by 2, and say the pulses are of magnitude 1. So e to the power of minus jn omega st dt. And this can once again be integrated, and what I get is 1 by ts, and this is e to the power of minus jn omega st divided by minus jn omega s, and the limits of integration being minus delta t by 2 to delta t by 2. And this makes it, if I absorb the negative sign, then I can, and I substitute the limits, it becomes e to the power of jn omega s delta t by 2 minus e to the power of minus jn omega s delta t by 2 divided by say 2j. I have a j, I multiply and divide by a 2. And what else is remaining is n omega s. Then what happens? The quantity within the bracket can be identified as a sine function. And so what we have is the Fourier series coefficients P of n is equal to 2 by Ts sine n omega s delta t by 2 divided by n omega s. Now, if I want to convert it to the sinc function, I multiply and divide by delta t. Then what happens is, and this 2 I can bring it below, and then I get it as delta t by ts sinc function of n omega s delta t by 2. So this is what we have as the final result, or the Fourier series coefficients p of n of my waveform. The signal which I use for sampling is given by sinc n omega s delta t by 2. So this is our, so now what is my output of, I'm taking my signal x of t and I'm multiplying it by p of t, and I get my sample signal xs of t. So so what we have is we have the signal x of t. This we are multiplying it by the pulses of finite duration, and we get the sample signal xs of t. So my xs of t is nothing but the product in time domain x of t into p of t, and I have my x of t. Now p of t is a periodic signal, and hence I use the Fourier series representation, which is an exact representation of any signal that is periodic in time domain, Jn omega st. And we just now have computed the value of, because I can just interchange the summation. I can have it as p of n x of t e to the power of jn omega st. And we have just computed the value of p of n. And what was that? Delta t by ts sinc n omega s delta t by 2. And then we have the remaining, that is x of t and e to the power of jn omega st. So if this is in time domain. Now if I want to have the equivalent in time domain, so in frequency domain, I take the Fourier transform of the above. We take the Fourier transform of above. And what we get is xs of omega is equal to, again Fourier transform satisfies the linearity property. So we have delta t by ts. This is a constant. So sinc n omega s delta t by 2. And x of t into e power jn omega st, we know has the Fourier transform x of omega minus n omega s. This is something we had seen in the previous module. So now what happens? What happens if I try to, suppose once again I consider my x of omega, the spectrum of my original signal x of t is a band limited to minus w to plus w. And how is my spectrum of my sample signal now? Xs of omega. This is going to be, say, minus w to plus w. The first value. What's my first value? This corresponds to put n equal to 0. Put 0, and sinc 0 is a 1. And hence we have delta t by ts and then x of omega. So I'm going to have a multiplying constant of this magnitude is going to get multiplied by delta t by ts. And how about, say, for omega s? I am going to have the value as delta t by ts multiplied by sinc n omega s delta t by 2. It's the same function, and this is a value, and that is going to depend on n is 1, but omega s delta t by 2 a constant, and this value will always be sin x by x always takes a value less than 1, and hence it is going to get multiplied by some term of magnitude less than 1, and that multiplied by this, and hence what we have is it's going to be of a magnitude less than the earlier one. And how much it's going to be reduced will depend on the value of Ts, delta T and Ts. So this magnitude is going to be lower than the earlier magnitude. And similarly, the next one. And the same function after it's either positive or negative, and it's always less than 1. And hence this is what we have. Of course, there will be other terms at 2 omega s, 3 omega s, and so on, plus or minus. It's not periodic now, but it still has the original spectrum x of omega, and x of omega shifted to omega s, to omega s, etc., but with varying amplitudes. Amplitudes decreasing with increase in omega s. At omega s, we have some magnitude. At 2 omega s, it's going to be even more reduced. So this is the spectrum of the sample signal when I use sampling by using a rectangular pulses instead of an impulse train. And now, once again, if I look at the spectrum, I can still recover my original spectrum x omega by passing it through a low pass filter. And once again, my low pass filter cutoff has to satisfy the same condition. Omega c should be greater than W, and it should be less than omega s minus 2. So this is our conclusion. So what we now conclude is, instead of an impulse train, if we use a pulse train, pulses of width delta t and time period ts, we can still recover the spectrum of the original signal by passing the sampled signal through a suitable low pass filter. The only difference is when I use an impulse train, all the spectrum of the value at x n equal to 0, that is x omega, x of omega minus omega s, and so on, all are of same strength. Whereas when I use a pulse train, there is a decrease in the magnitude of every shifted component. So maybe we'll take an example. To understand the result. So the result that we have is xs of omega. The spectrum of the sample signal is sigma n equal to minus infinity to infinity delta t by ts sig n omega s delta t by 2 and x of omega minus n omega s. For example, let us take the situation wherein my pulse train P of t is going to be say delta t, and then I have another pulses of width delta t. Sorry, the pulses of width delta t and time period ts. And let's take the case, say delta t is 0.1 times. Let us take the case where delta t is say 0.1 times ts. So that is delta t is only 10% of the width of the ts. So then what we have, in this case, what happens to our spectrum of the sample signal? Excess of omega is sigma n equal to minus infinity to infinity. Now I have my delta t by ts. This quantity is now 0.1, 0.1. And then I have my sink n omega s delta t by 2 and x of omega minus n omega s. What is this quantity? What is this quantity? Omega s. Let us look at, say, omega s. N times omega s delta t by 2 is nothing but n. Omega s is 2 pi by ts, and this is delta t by 2. And delta t by ts we said is 0.1, and the 2 gets cancelled, and so in this particular case it becomes 0.15 n. So omega s is 2 pi by ts, and then delta t by 2, the 2 gets cancelled, and delta t by ts, we are taking the case that we are considering delta t by ts is 0.1. And then this is what we have, and hence we have our spectrum of the sample signal equal to sigma n equal to minus infinity to infinity, 0.1, sink 0.15 n, and x of omega minus n omega s. This is our spectrum. So now if I want to sketch the spectrum of my sample signal, what happens? Xs of omega at put n equal to 0, since 0 is a 1, and so I have this of strength 0.1. Of the strength 0.1 extending from minus w to w. And what happens at n equal to 1? I need to compute sink 0.15. Let us calculate what is sink 0.15, and then we will know the magnitude. Say x equal to 0, 1 into pi, n equal to 1. So this, and my sink is nothing but sin x by x, and I get the value as 0.98. Similarly, if I put n equal to 2, it is going to be my x will now be 2 into 0.15. So that will be, and the next value is going to be 0.93. So the magnitude gets reduced with increasing. So instead of 0.1, it's going to get 0.1 multiplied by 0.9. So the magnitude reduces, but the width will remain the same. So depending on Ts or the ratio of delta T by Ts, the spectrum of the sample signal is going to change, and we can once again pass it through a low pass filter and get back our original spectrum. So the conclusion is, even instead of an impulse train, even if I have pulse train, we can still recover the original. We can still continue with sampling and get back the original signal from the sample signal. A recovery is possible from the samples. So that is so this solves the problem of this, addresses the problem of pulses. So next case that we shall take is we shall try to go into another concept, that is aliasing. The concept of aliasing. We will try to see what exactly this is, and do we have band limited signals, and what happens if we do not have band limited signal. So now let us take once again an example, and our aim is to understand the concept of aliasing, and we'll see what is aliasing and why does the problem arise. So for this we'll take some 1 or 2 examples in Fourier transform. Let us take an example, say x of t. Say x of t. Say the same signal that we saw yesterday of magnitude 5 in the previous module, and what was the Fourier transform of this function? We obtained the result as 5 fours are 20. The area of this pulse 20 and sync 2 omega. And how is the spectrum going to be? It has a magnitude of 20 and 0 crossings at 5 by 2. 5 by 2 multiples of 2 omega equal to 5. So 5 by 2 minus 5 by 2 and so on. This is our spectrum of the sample of the rectangular pulse. Now what I will do is I will try to have the same. I'll have another signal say y of t. I will try to compress a signal in the time domain. So I retain the magnitude as 5, but I make it go from -1 to +1. Say -1 to +1 and magnitude remains at 5. Now what do you think will be it's always the area of the rectangular pulse. So the area of the rectangular pulse is 5 to the 10. So in this case, my y of omega is going to be 10 sync and 5 omega into 1, so sync omega. Now let me try to plot the spectrum of the sample signal. Now where is my 0 crossing? 0 crossing is going to be at integral multiples of omega equal to 5. My first 0 crossing will be at 5. The second will be at 2 pi, minus pi, and minus 2 pi. And the strength is now, earlier the strength was 20, now the strength has become 10. So how is my plot going to be? In this manner. So I have, so what does this show? This example shows that if I try to compress a signal in the time domain, it results in an expansion in the frequency domain. So we cannot compress a signal in simultaneously in both domains. Compressing in one will result in an expansion in the other domain. Similarly, if I do an expansion in the time domain, it will result in a compression. We can take one more example if required. So say I take another example, say z of t, and say this goes from say -4 to +4 and a magnitude of 5. Then its Fourier transform z omega is going to be area of this 8 5s are 40 sync 4 omega, and hence what is my spectrum going to be? 40, and where is my 0 crossing going to be? At omega equal to 5 by 4. See now at 5 by 4, this is 5. So it's the spectrum. Of course, I need to draw 40 of a higher amplitude, but then this is what is going to be. So what has happened? We try to expand the signal in the time domain, and that immediately results in the compression in the frequency domain. This property is contained. This property of any signal is contained by what is known as the time duration. The product of any signal, the time duration and the bandwidth, is always greater than or equal to half. So this that is expansion in one domain results in compression in the other domain. So now let's take once again the same rectangular pulse, say x of t. X of t. This is time limited, so I have it as say -2 to 2 and 5. And we know this has a spectrum. X of omega is equal to 5. 4s are 20 sync to omega. And it's in the frequency domain. The plot was at 5 by 2, 5 minus 5 by 2 and so on, a strength of 20. This is what we have. Now, if I look at the spectrum, a sync function, how is the signal? This signal is time limited. And how is it in the frequency? If a sync function doesn't die down to 0, unlike an exponential function which dies down to 0, this magnitude keeps on decreasing, but it does not tend to 0. It keeps decreasing. and hence it is in principle it has a large frequency band. It has a large frequency band. Now let us I do not try to do any I know sampling theorem, but I just decide to ignore, and I will just take some sampling interval. Let us say I take a sampling interval ts is equal to say 1 second. I take a sampling interval ts equal to 1 second, and I multiply it, and I try to get a sequence x of n. So I take a sampling interval. So this I have -2, -1, and then at 1 and 2. And all are going to be of strength 5. So what did I do? I did not put any efforts in actually applying my sampling theorem, and I simply took samples. I just randomly decided, okay, I will take a sampling interval of 1 second, and then I do. And this is my sample signal. And how is the spectrum of the sample signal? By our knowledge of sampling, the spectrum of the sample signal, what will be my excess of omega now? So what is my Ts is equal to 1. So what is omega s is 2 pi by Ts, and that is equal to 2 pi because Ts equal to 1. And how is my original spectrum? And we have my original spectrum at pi by 2, 0 crossings at pi, 3 pi by 2, 2 pi, minus 2 pi, and it has a magnitude of 20. What is this component? What is the spectrum of our sample signal? We know that excess of omega is equal to sigma n equal to minus infinity to infinity 1 by Ts x of omega minus n omega s. Of course, this gets multiplied by Ts, and 1 by Ts in this case is a 1, so it remains as a 1, and this is what I have. The first component is what we have drawn, x of omega. How about the second component? I need to draw for n equal to 1, x of omega minus omega s. And what is omega s in this case? It is 2 pi. So I need to draw, say 3 pi, and I need to draw the same spectrum. And similarly, if I take n equal to -1, x of omega plus omega s, I'm going to have the same spectrum that is going to occur. So, and similar, this is for, and if I take n equal to 2, x of omega minus 2 omega s, that is nothing but at 4 pi, 3 pi, say 4 pi. So once again here I'm going to have the component because of n equal to 2 minus 2 pi, say minus 3 pi, and say minus 4 pi, and I'm going to have now what happens? We see there is the original spectrum. This is my original spectrum, x of omega. This is omega minus. This term corresponds to x of omega minus omega s, and this term corresponds to x of omega minus 2 omega s. And my original spectrum x of omega is here. And similarly, this term corresponds to x of omega plus omega s. And now what happened? There is a significant overlap in my original spectrum and with the spectrum of the sample signal. And so I will not have this. Eventually, what will happen? If I try to draw excess of omega, my spectrum of the sample signal, I am going to have the equivalent result. It's not going to be like both. So they will, eventually I will have some plot that is, I'll have here, and probably it will tend like this. So what does this example show us? And no matter which low pass filter I use, I am not going to be able to recover the signal because I have used a sampling interval very, very large. I have taken a sampling interval Ts equal to 1 in this case. And when I took a Ts equal to 1, this is what I get. And this is my spectrum of the sample signal. Now, what are we observing? So we have taken an incorrect sampling interval. We have taken a large sampling interval. That is a very small sampling frequency. A sampling frequency small. And what has happened now? Let us say I try to, if I use omega s is equal to 2 pi, I need to have a low pass filter whose cutoff is going to be pi. So what happens now? What are we seeing? This is my desired spectrum. In the desired spectrum, I am having the overlap of what are these components? The high frequency components of the shifted spectrum. The high frequency components of the shifted spectrum. So we have an overlap of the high frequency components of the shifted spectrum in our desired band. This overlap of the high frequency components in the desired band is what is known as aliasing. Aliasing, and that is the high frequency components of the shifted components of the sample spectrum coming into a desired band causes a distortion, and the distortion cannot be removed by any type of filtering. Results in distortion. So we cannot get back the original signal without any error. So the recovered signal is going to have a significant distortion, and this depends on the amount of aliasing. And how do we avoid aliasing? Aliasing, of course, one method is to increase the sampling frequency. One method is to increase the sampling frequency Fs or to decrease Ts. For example, in the same case, instead of if I consider the same example, I had my signal x of t, and this was going from minus 2 to 2 with a magnitude of 5. Now I decide to choose my sampling interval Ts is equal to say 0.25. And then what happens now? My sequence xn, if I take my sampling interval Ts as 0.25, I am going to get 1, 2, 3, 4, 5, 6, 7, 8. So this is what I have. I have large number of samples for the same signal. All that we have done is we have reduced our sampling interval Ts. And by doing so, now what happens to my omega s? My sampling frequency omega s is now 2 pi by Ts. Ts is 0.25, that becomes 8 pi. And hence what happens to the spectrum of my sample signal now? Xs of omega is sigma n equal to minus infinity to infinity 1 by Ts x of omega minus n omega s. And omega s in this case now becomes 8 pi, and hence the spectrum of my sample signal xs of omega, we had the zero crossings at pi by 2, pi, and the strength of 20, minus pi by 2, and so on. And now I reduce my sampling interval. So my omega s has now this say pi, 2 pi, 3 pi, 4 pi, 6, 7, 5, 6, 7, and 8 pi. And I have my x of omega minus omega s now has shifted quite far away. And similarly, I'll have the other component x of omega plus omega s shifted to 8 pi. So do we see the advantage? And now I can to recover my signal, I can use a low pass filter with cutoff anywhere. So even if I use a cutoff of around, typically low pass filter cutoff, we can set it to half the sampling frequency, so 4 pi. So now I have significantly avoided aliasing. But however, there is still small strength in strength of my shifted spectrum likely to come into my desired band. It may be low, but it is likely to be there. And hence that what we can do is, instead of taking my signal x of t and directly multiplying it by p of t, I'll pass it through a low pass filter. Say I pass it through a low pass filter with a cutoff of say 4 pi, which is nothing but omega s by 2. Whatever sampling frequency I decide, and then I multiply it by p of t, then I get my x sampled signal. So then what happens is, we are ensuring that my input signal does not have frequencies beyond omega s by 2. Of course, this is we can choose any other frequency instead of omega s by 2. I could also choose it as omega s by 3 or omega s by 4, but it has to be definitely less than the cutoff frequency of my low pass filter. The low pass filter cutoff frequency, the say omega A, the low pass filter cutoff frequency that is used has to be less than omega s by 2. Any reasonable cutoff that we can think of, but has to be less than omega s by 2. Then I multiply it. Then what happens is, we are ensuring that all frequency components above omega s by 2 are eliminated, and hence we do not have the problem of aliasing. So aliasing and hence this low pass filter is also known as the anti-alias filter. And why do we pass it through a low pass? We saw that if I have a signal which is limited in time, it is going to be unlimited in frequency. So there are going to be small frequency component strength, but small frequency strength, high frequency component being present in the signal. And that leads to an overlap in a desired band. And this can be removed by simply passing the signal through a suitable low pass filter before sampling. So any input signal, we pass it to a low pass filter of frequency, that is cutoff frequency less than omega A by 2, omega s by 2, and then do the sampling operation through a rectangular pulse or through an impulse train. And then we get the sample signal, and at the receiver we take the samples and then get back the pass it through a low pass filter, and we get back the original message. So let's take one more small example to understand the aliasing, the problem of aliasing. Let us take, say my signal x of t is cos 10 pi t. So this is a signal of frequency of omega equal to 10. This is a signal that has omega equal to 10. And if I were to follow my sampling theorem, my omega s should be greater than 20, because greater than twice the band contained in my input, and so it should be greater than 20. So now let us consider the case that my sampling frequency, let me set my sampling frequency omega s equal to say 40. I set my sampling case 1. Case 1, I set my sampling frequency omega s equal to 40. And if I put my sampling frequency omega s equal to 40, let us see how is the spectrum of my sample signal and how is the original spectrum. Let us see my original spectrum. We know this is, it has an impulse at, omega equal to, omega equal to 10 pi. Greater than, sorry for that. Omega is, say, omega is 10 pi. At 10 pi, I have an impulse. And I have another impulse at minus 10 pi. This is my spectrum. Now, if I set my sampling frequency to 40 pi, what happens? The spectrum of my sample signal, excess of omega, I am going to have enough number of samples, and then I am going to have my spectrum of the sample signal. And my original spectrum I have as such, say in case of an ideal sampling, minus 10 pi of magnitude pi, and then 10, say 20, 30, 40. So the component corresponding to x of omega plus minus omega s, that is for n equal to 1. At 40, I will have the spectrum, the whole original spectrum shifted here. So I'll have the component at 30 pi and then 50 pi. Similarly, minus 10, minus 20, minus 30, minus 40. This is the spectrum of my sample signal, and I can comfortably get back my original signal by passing it through a suitable low pass filter and of frequency greater than 10 pi and less than 30 pi. Now let me take another case, second case, say case 2. I know my sampling frequency for this case has to be greater than 40 pi. I mean greater than, sorry, my signal x of t is cos 10 pi t, and by sampling theorem my omega s should be greater than twice, that is 25. But I do not take 25. What I decide, I simply try to ignore the sampling theorem, or I'm not aware of the sampling theorem, and I decide on taking omega s equal to say 15 pi. Now let us see what happens to the spectrum of the sample signal. So I'm setting my sampling frequency to 15 pi, and let's try to sketch the spectrum of my sample signal. What's my original spectrum? I have say 10, 20, 30, 40, 50. So 10, 25, 10 pi, 25, 35, and so on. And minus 10 pi, minus 25. So at I have my original spectrum here, x of omega at, because my signal is of and magnitude pi. This is my original spectrum x omega. Sorry, now I put my sampling frequency as 15 pi. So what is my component now? My sampling frequency omega s is 15 pi. So my original spectrum gets shifted to 15. So from 15, it is going to be a component plus 15. So at 25 pi, I'll have a component, and I'll have a component minus. So at minus 5. Similarly, I have my sampling frequency at minus 15. So plus 5, I mean plus 10 and minus 10 pi. So this is my component. And now if I choose my sampling frequency of omega s, and let us say I choose my cutoff frequency for recovery, what happens now? This is a component that is present at 5 pi. This green component is my component omega minus omega s, and of course here also, here it is omega x of omega plus omega s. Now if I pass the signal through a low pass filter, and say I choose a low pass filter of cutoff, usually we choose a cutoff at a half of omega s, so 15 pi, so around say 7. I choose my omega c, my low pass filter cutoff as 7 pi. Now what happens? I do get a cosine wave. I do get a cosine wave, and but what is my cosine frequency of my cosine wave? My output of the filter, my recovered signal is going to be cos 5 pi t. Please remember, we started with the signal. What was our original signal? Our original signal x of t was cos 10 pi t, and we incorrectly used a sampling frequency of 15 pi. although I know that I'm supposed to take a sampling frequency greater than 25, but I take an incorrect sampling frequency of only 15 pi. And when I do 15 pi and then I pass my sample signal through a low pass filter whose cutoff omega c is 7 pi, by looking at the spectrum, what I see is my recovered signal is going to be an incorrect signal cos 5 pi t. It is completely error. I started with a frequency, I did sampling, and then to recover my signal, I pass it through a low pass filter. I get an output, but the output is incorrect. And why has this happened? This has happened because, as I said, the high frequency component of my shifted spectrum comes and overlaps within my desired band. And that is why the initial frequency of 10 pi t, 10 pi has come and it is getting recovered as a signal of 5 pi. This is aliasing, and hence it is extremely important that we are aware of sampling theorem and we ensure the correct sampling frequency, and only then we will be able to get back the original message from the sample signal. Otherwise, we'll end up with a distorted output or incorrect, which is nothing but getting incorrect frequency components from the sample signal. And now, by one more short discussion, when we have seen that the sampling frequency should always be greater than twice W. So for any recovery, we always want the sampling frequency to be greater than twice W, where W is the highest frequency component present in the signal. As a general rule, we usually set it as greater than or equal to. But if suppose I have my, when do we use equal and when we are not allowed to use the equal? The condition is if my x of omega is such that the spectrum dies down to zero, as in this case, then I can use my sampling frequency omega s greater than or equal to 2w. On the other hand, if my original spectrum x of omega does not die down to zero, say minus w to w, but it has a significant non-zero value. In this case, I need to take omega s greater than 2w. That is, equal to is not allowed. Why? Because my x of omega is not equal to 0 for omega equal to w. So it does not die down to 0. It's a non-zero value. And in these type of examples, my sampling frequency has to be greater than 2w. For this clause, we'll take one very simple example. Let us say my signal is say x of t is say cos 2 pi t. So here I have an example of omega equal to 2 pi. And how is my cosine signal in the time domain? I have it as it is a cosine signal, and what in this particular example cos 2 pi t, my period of my this is 1, 2 pi by t, and t is 1. So this is a cosine signal of period 1. And if I choose to take my sampling interval ts exactly equal, I mean that is if I take my omega s equal to 2, twice the initial frequency, then I need to take two samples, exactly two samples and I may end up in the two samples being exactly 0, and I cannot recover my cosine wave from the sample spectrum. And hence there is a need in this case. And why is this case important? Because this is the case where my spectrum is not 0 at omega equal to pi. So in this is an example. If I sketch the spectrum of this signal, the cosine function, we know it exists at, in this case it is 2 pi, and of course magnitude is 5. So this is our spectrum, and the spectrum is band limited to 2 pi, but it is non-zero. And because of which we need to have at more than 2 samples being taken in every period of the sinusoidal signal. Uh, the reason is because of this. So as I said, if the spectrum dies down to 0, then we may take greater than or equal to. But if the spectrum does not die down to 0, then our omega has to be greater than 2 the. So I think we will, again, the reference for the content covered today is from the book Signals and Systems by Simon Higgins, and the other book, Principles of Communication Systems by Tom Schilling. And having seen today, what we have seen is aliasing results in distortion, and this can be avoided by passing the original signal through a low pass filter before performing sampling. And when I use pulses, short duration pulses instead of an impulse, I can still recover my original spectrum from the spectrum of the sample signal by passing it through the low pass filter. So even though it's ideal to have an impulse rate, pulse rate does not cause any distortion. All that happens is the components of the shifted components, the strength decreases, and we are not interested in the magnitude of the shifted components. It's the original spectrum x omega, and hence we can still recover. So if I use pulses, pulse train, pulses of finite duration, I can still get back my signal. And similarly, I can also get back my signal I can avoid aliasing by using a simple low pass filter before performing the operation of filtering. So thank you. In the next module, we shall see the sampling of band pass signal. Band pass signals, like if I have a band pass signal, then how is my sampling frequency? That is, if I take my x of omega, say it extends from say omega L to omega H. If I have a signal like this, what should be my sampling frequency? Can I attempt to have a lower sampling frequency because it's a band pass signal and not a low pass signal? So far we have seen how to compute the sampling frequency for low pass signals. Now let us see if I use a band pass signal, how to compute the sampling frequency. This is what we shall see in the next module. And this will be followed by a practical, an experiment, a simple experiment to perform sampling, to see a sample signal and then attempt to recover the original signal from the sample by passing the same through a low pass filter. Thank you.